Hi everybody. I just wanted to give you a brief rundown about a new lecture that I've devised called Make It Count. In the Make It Count lecture, what we're going to do is we're going to devise a simple SR latch, describe its behavior, then show you how you can get a T-latch, a D-latch, and finally how you can clock the latch. Let's start with a simple SR latch using a cross-coupled NAND gate. We'll call this S and R, and we'll call this Q and Q prime. The SR latch is generally unstable when you stimulate both inputs at the same time with a 1. Let's describe its behavior in terms of the present state and the next state. We'll use the plus sign to show the next state. So here, if we're in state 0, we're reset, and we want to stay reset, we have to make sure that the SR stimulations are such that set is not set, and reset, we don't care what it does. It could be asserted to 1, that would cause us to reset, or it could be asserted to 0, and that would allow us to maintain state. Similarly, if we're in the set state, we really don't care what the set state does as long as we don't do a reset. In other words, if we say reset is 0, set could be 1 or 0, it doesn't really matter, and we represent that don't care with an X. Next time we look at 0, 1, we want to put into a set state. We want to make sure we don't reset. Here we want to put into a reset state, which means we want to make sure we do not set. And that describes the excitation table for the SR latch completely. And it's done with just 2 NAND gates. Now let's take a look at the T-latch. The T-latch is a little bit different. We'll just make a little diagram of the T-latch, and we'll show that it has a single toggle input with the same state and inverted state on output. And what we can do to describe it, we show the input and the present state, and we say if the toggle is 0, the present state does not change. So here we see toggle input is 0, state does not toggle, so for the next state we write 0. We stay with 0. Here we're in a 1 state, we remain in the 1 state. Here we say we're going to toggle, so 0 gets turned into a 1. Here we say we're going to toggle, so a 1 gets turned into a 0. And now we see what the SR inputs should be in order to make these transitions occur. So to go from 0 to 0, that is 0 to 0, it's 0x on input. To go from 1 to 1, it's 1 to 1, it's x0 on input. To go from 0 to 1, we want to do a set. So here it is, set, that's 1, 0. And to go from 1 to 0, that we need to do a reset. And so here it is, 0, 1. And what that tells us is simple. It says that S must be equal to TQ prime, and here's S, and there's T and Q prime, and R must be equal to TQ. And so we can arrive at an SR latch where S is the inverse of R, or R is the inverse of S, and S is going to be T, Q prime, or TQ. Let's take another look at what we just did. We used the excitation table for the SR latch. We wrote out the way we think toggle flip-flop should behave. We used the excitation table to say what the inputs need to be for S and R. We backed out the equations for S and R so that we could obtain the behavior that we were looking for from T and Q. So T and Q went in to S and R using the combinational logic that we derived from the truth table, and that allowed us to use a T flip-flop simulated on top of an SR latch. Let's do this again. We're going to do a D latch. Now the D latch has a simple delay input, and whatever goes in must come out 1 clock cycle later. In this case, 1 delay time later. And so what we're going to do is we're going to describe the D latch just like we did before. We'll go D and Q instead of T and Q. And what we'll say is the output for the next state is going to be equal to the input on the prior state. And now we can write out the SR latch inputs. So to go from 0 to 0, just like before, we use 0x. To go from 1 to 1, just like before, we use x0. And now, if what you want to do is reset the flip-flop, you need 0, 1 on input. And if what you want to do is set the flip-flop over in here, you need 1, 0 on input. So what that tells us is that S is equal to D, and that R must be equal to S prime. So now I can make a D flip-flop from an SR flip-flop, or an SR latch if you like. Run the inverter across, and the input will be D. And now when D is equal to a 1, that'll set, reset will be 0. When D is equal to a 0, set will be 0, reset will be 1, and it will reset. The only thing that remains for us now is to add a clock. And what we'll do is, for the T, we'll just use a level trigger clock. And we'll put that into our T latch. Similarly, for the D flip-flop, we'll just make a level trigger latch input for the D flip-flop, and that'll give us a piece of clocked logic. Clocking won't be as clean as you might like if you had a master-slave relationship, but now you've got a mechanism that's going to enable you to effectively design T and D flip-flops from something as simple as an SR latch. Hope you liked my little video. Thanks a bunch. Bye-bye.